Hi everyone, my name is theorize. I'm a junior at the University of Florida, junior undergraduate. My major is astrophysics, and I'll be presenting what my research is so far in the McNair open house. So I'm doing this virtually just because I'm not here in person. So I'll try my best to explain what I'm doing over the video. But if I have a hiccup here or there, then I'll try my best to go over it. So my research is investigating ammonia majors in the W51 star forming region. So W51 is one of the most luminous and most active star forming regions in the galaxy. Within W51, there contains numerous astrophysical majors. So majors are essentially the excitation of molecules. You can think of it as a laser in space. So these majors are essential in star formation because in literature they trace star formation processes like disks, like accretion disks and outflows. However, in the literature, there's also all the so the ammonia majors, they are specifically good in tracing high mass star forming regions. But in the literature, the locations of these majors are not well constrained, meaning that they're not readily accessible in, let's say, a chart. So in this research, this is what the research is about, is to find the spatial locations of the ammonia majors in W51. And it also gives me a unique opportunity to study the spectral components of the majors, such as the velocity, the brightnesses, and those velocities include the local standard of rest velocity and the line widths of each major. So knowing about the majors are essentially very important in star formation because they trace those processes, the star formation processes. But studying these majors can give us more insight in how our own galaxy and solar system came to be and how they formed, along with other similar stars and star systems. So let's get into the observations. What exactly did I do for this research project? So far, basically I had to start from the ground up. So I had to start from the VLA telescope, so the Very Large Array Telescope. All the data, I had to process all the data in the K-band I had to search for all the data in the K-band for potential major candidates. So the reason why we're looking at the specific region of the sky, W51, and in the radio K-band is because of a previous proposal by my mentor, Dr. Ginsberg, and I think by Henkel or Gotti. So they assumed that there's going to be some ammonia lines within. Well, they knew that there was going to be some kind of ammonia lines within the K-band, and they kind of knew that there was going to be majors here, but they did not exactly where and what the spectral components were going to be. So essentially, I had to process all the data, the raw data, and before I had to do any measurements, I had to clean it. So I had to use the T-clean algorithm to get rid of all the dirty images and make the images so that I can observe from it. So that took a while. I had to search through each channel. I had to clean basically all the data. And then afterwards, then I can actually start observing exactly what the different majors are, or I'm searching for the ammonia majors. And after I cleaned the data, essentially, so I had to search each channel. I had to essentially sweep through the whole frequency for major candidates. So there are 3 criteria where I would consider a major. So when I'm searching through the images, it has to be a point source object. It also has to have a very high brightness temperature, which indicates the major's non-local thermodynamic, no, non-local, I think it's non-local thermal equilibrium. I'm not too sure, but very high brightness temperatures basically indicates major properties. And the line width has to be very narrow. So if all three of those criteria are correct, then I can say that whatever I'm looking at is a major. So I have to do that for the entire frequency of the K-band. And afterwards, I found, after I did my entire sweep, I found 10 major transitions, which were the 5-3 lines, 6-2, 6-3, 7-4, 7-5, 7-6, 7-7, 8-5, 9-5, and 11-9 major transitions. So after I observed all of the majors and cataloged all of the before I go on, for the observations, I used 1D Gaussian fits and 2D Gaussian fits using the Python libraries PySpecKit and AstroPy.modeling, and I had to guess the fits for all of them, and that essentially gives me the measurements and the errors, which I have to calculate for 2D Gaussian using the covalent matrix. So I use 1D Gaussian for the brightnesses and all the velocity measurements, and I use the 2D Gaussian for all the spatial location measurements. So here's what I got from that. After I got all the data, all of my observations, now I have to try to make charts to visualize what my data means. So in the middle plot, figure 2.1, you can see that there's three regions actually. So CA3 in the top left, which is a previously unidentified region that we named this summer. In the middle, that's the entirety of W51 North, and there are two Ammonia 11-9 lines, which we're getting to in a little bit, and D2, which is a hypercompact H2 region believed to emit free emission. So D2 is interesting because my measurements indicates that there's three particular regions that has clusters of different ammonia transition lines. So I can't really conclude anything based off this information yet, but it is important to note that there is three different areas where the majors are, because with comparisons with older positions, with previous positions, I can map exactly where the majors are moving, which can indicate something like uniform circular motion, but I can't conclude that as of yet. In the middle region, where W51 North is, there is two 11-9 major transitions. Yes, okay, so there's two yellow, it's essentially the yellow crosses in the middle section. There are two 11-9 ammonia lines, ammonia majors, and essentially the positions of the majors correlate exactly with previous literature from Ginsberg, Gotti, et al. 2020, and they correlate with the two different lobes of outflow. So the major positions are exactly right on top of the majors. So the positions of the majors correlate exactly with the outflows in that region, the different lobes of outflow. So this can just provide more evidence that the presence of ammonia majors, which can also indicate the early evolutionary stages of star formation in protostars, they just essentially further provide evidence that there's activity in these regions, that there's actually outflows in these regions. Additionally, the CA3 region, all there is right now is there's a whole cluster of different ammonia transitions within one singular region. So we can't exactly indicate anything just from these measurements, but it is important to note the spatial velocities for future research and future comparisons to actually try to map the physics of what the masers are doing. So for the next thing I did was compare all of my velocity and brightness measurements with Hankel's 2013 paper. And essentially with that, all the velocities over time, and this is from 2012 all the way to 2013, which was when my data was recorded. 2012 is when Hankel's data was recorded. Essentially from this, all the velocities, the local standard for res velocities, and the brightnesses are highly variable, meaning that they essentially shift over time. So this basically proves that there's some kind of motion within the masers. There's some kind of motion in the star forming regions, but we can't exactly say for sure what kind of motion it is. Let's say, for example, if it's uniform circular motion, if the masers are in the outflow, or if it's from any type of other motion. So we can't say for sure, but all we know is since the masers themselves are moving or shifting in velocity over time, that means that there is some movement happening. And likewise, with the change in brightness, brightnesses over time, that essentially means that the masers are being radially pumped from some source, and that source is believed to be what I think it is. It's probably the protostar. So depending on its distance away from the protostar, the masers itself are going to get either less or more energy from the star. And I think that's essentially what radially pumped is for a maser. And all masers needs to be fueled in space by some source. So it just confirms that, hey, these masers are circling some kind of source, which is believed to be a protostar. So afterwards, I just cataloged all of after that, I decided to make color velocity plots in respect to the positions. And you can kind of see that in figure 2.2 and figure 2.3. So here, essentially the VSLR and the D2 region, so the D2 region here, they have higher velocities than in the CA3 region right here. So that just simply means that the masers themselves are moving at a faster velocity in respect to Earth's perspective than for, say, the CA3 region. But that doesn't necessarily mean that the cloud itself is moving away at that velocity. We just only could observe that the masers themselves are moving at a faster velocity than the masers in the CA3 region. Likewise, some of the masers in the D2 region are significantly brighter than the sum of the brightnesses. Well, not the sum, but some of the masers in the D2 region are brighter than in the CA3 region. So this is just something to note, but it doesn't necessarily mean that there's any astrophysical properties linked to the brightness of the maser and the brightnesses of the region themselves, or anything to do with the region. But it is important to note that the D2 region itself, the hypercompact H2 region itself, is significantly brighter than the CA3 region. So before I move on, there's one more thing I want to point out. So the 6,3 ortho ammonia line. So with that particular line, when I shifted through the different frequencies, when I looked through each channel of frequency, it exhibits interesting property. So between each major, well, not each major, in between each channel, the actual major spot itself, it moved as I shifted through the different channels. So this can indicate some type of velocity gradient, but I can't be completely sure exactly what it is as of yet until I apply a further analysis to that. And I made a position velocity diagram plot, which is not shown in the poster. Now, after all of that, I wanted to dig a bit deeper into the W51 CA3 region. This W51 CA3 region, we don't really know what it is. So we know what the D2 region is. It's a hypercompact H2 region believed to be, which it believes to emit the free emission, but and also to note that the D2 region, it is heavily cited in literature, but the CA3 region, we don't know what it is exactly. It could be a hypercompact H2 region, but we don't know if it's what kind of emission it's giving off. What if it's free emission, if it's dust thermal emission, or if it's just synchrotron emission, which is less likely than the others. But to exactly know what kind of properties, what are the properties of the CA3 region and what emission it's giving off, I've made a spectral energy diagram to essentially tell what kind of emission it's giving off. So essentially, based on the graph you see in figure 3.1, based on the slope of the blue line, to my extent of knowledge so far, based on the slope of the graph, it can tell you whether if it's synchrotron emission, if the slope is negative. If the slope is negative, it can be synchrotron emission, and based on how positive it is, it can be either free emission or it can be dust emission based on the shape and the slope of the lines. But this particular graph or this particular diagram needs a further analysis, or it needs better data because I haven't used the primary corrected beam. The primary corrected beam, which essentially would give me more accurate fluxes with each of the frequencies. And just to explain what the graph means really quickly, each frequency is a different band in the VLA telescope or the ALMA telescope, the ALMA radio telescope. So I basically calculated the fluxes of the CA3 region for different frequency and different continuum images with different frequencies over the VLA data and the ALMA data. So this leads me a little bit to my future work. So I want to try to make the spectral energy diagram a little bit more accurate using the primary corrected beams. So I have to find the primary corrected beam images and applied it to the spectral energy diagram so I can accurately conclude what kind of region W51CA3 is. Also, for my future work, I plan to calculate the proper motions of the ammonia masers. So that essentially means I want to calculate exactly where masers are going from one point in time to another point in time. And I need to shift to the literature to see if there's any locations, because the locations are well confined or well constrained in literature. And also want to apply different techniques to kind of make a better discussion and conclude on the data I have. So I made observations and I made charts and some analysis, but now it's time to get everything together and actually kind of get some meaning of the data I have, and what story does the movement of the masers play or tell in the star formation in respect to the star formation region, whether the star formation in these respective regions, whether the processes are mass accretion or outflows. So I want to kind of write the story of what story does the masers tell? That's what I'm trying to say. So that's my future work, and you can see my references in the bottom right of my poster. And for my acknowledgements, I'd like to thank my research mentor, Dr. Adam Ginsberg. I'd like to thank the Ronald E. McNair Post-Bachelor Achievement Program. I want to thank those two specifically, and I just want to mention the NSBP grant that funded the research for getting the data in the first place, and also all the previous effort into getting the data itself. So yes, that's it for my poster presentation, and I hope you enjoyed. See you later.